Welcome to Budesonide Solution Metered Dose Inhaler Plasma Treated Canister Performance and Other Canister Types. I'm Dave Lewis. I'd like to thank my co-authors Rob Johnson and Daniel Lewis from Oz UK Limited, Chippenham, Wiltshire, UK, and Jacqueline Green from HT Press Part, Blackburn, UK. The key message in this presentation is that an ethanol-based budesonide solution HFA-134A metered dose inhaler has been evaluated in 5 alternative canister types. The chemical stability of budesonide is observed to be directly dependent upon canister choice. Budesonide is used in the management and treatment of inflammatory diseases including asthma and COPD. Early administration of inhaled budesonide is reported to reduce the likelihood of needing urgent medical care and reduces recovery time from COVID-19. The importance of selecting a suitable canister during formulation development has previously been highlighted. Chemical degradation of budesonide within ethanol-based HFA-134A solution formulations has previously been reported when packaged in non-surface treated canisters. In this study, a budesonide solution formulation is packaged in 5 alternative canister types. The top 3 canisters listed here are surface treated canisters: fluorocarbon polymerized plasma coated FCP, anodized, fluorinated ethylene propylene FEP, and plain canisters, stainless steel and aluminium. All canisters were provided by Presspart Manufacturing Limited. In this study, in vitro drug delivery and chemical stability data are presented from 3 time points: the time 0 data, the initial, and following storage at 1 month at 40 degrees 75% relative humidity, and 3 months at 40 degrees C and 75% relative humidity. Solution metered dose inhalers are manufactured by weight. Each canister contained budesonide 50 micrograms per 50 microliters. Canisters were crimped with Aptar valves and gassed with HFA-134A propellant. All inhalers contained 13% weight-by-weight ethanol. Canisters were stored in Vinden scientific stability cabinets. Drug mass was recovered from each metered dose inhaler by evaporation of the propellant and the solvent and quantitative rinsing into volumetric flasks. Analysis of test sample content was performed by a verified HPLC assay. Results are presented as a percentage of the initial drug residual can content immediately following manufacture. Budesonide degraded significantly within the uncoated stainless steel and aluminium canisters. Values as low as 62 and 79% were observed in stainless steel and plain canisters respectively. For the surface treated canisters, plasma, anodized and FEP, budesonide residual was above 97% when stored valve up after 1 and 3 months storage at 40 degrees C and 75% relative humidity. For surface treated canisters, budesonide residual was observed to be 1 to 2% lower if stored valve down. A detailed discussion regarding the valve selection for this study is out of scope for this abstract. Drug delivery characterization was performed at a sampling flow rate of 30 litres per minute using a next generation impactor fitted with a USP induction port. Budesonide drug delivery performance was evaluated for formulations packaged in plasma-treated canisters immediately after manufacture and again following 3 months storage upright at 40 degrees and 75% relative humidity. No significant difference was observed in the budesonide drug delivery metrics: delivered dose, metered dose and fine particle dose less than 5 micrometers aerodynamic diameter. This graph presents a cumulative budesonide mass undersize. We can see that the dose less than the aerodynamic diameter of 5 is equal to approximately 20 micrograms for both initial and 3 months time points. Presenting the cumulative budesonide mass undersize as a percentage on the y-axis allows us to read 50% to give us the mass median aerodynamic diameter approximating to 1 micrometer for both initial and 3 months time points. In conclusion, the data presented in this study highlights the importance of selecting a suitable canister type during formulation and product development. For the budesonide formulation evaluated in this study, surface-treated canisters outperformed plain stainless steel and plain aluminium canisters. With regard to drug delivery performance, plasma-treated canisters showed no significant difference for budesonide drug delivery metrics, delivered dose, fine particle dose and mass median aerodynamic diameter before and after 3 months of valve-up storage at 40 degrees C and 75% relative humidity. And here are the publications referenced in this presentation. I would like to thank you for watching this presentation, and I would like to thank the Drug Delivery to the Lungs Committee for inviting us to present. And finally, if you'd like to contact us or ask any questions, please find our details on this slide.
Welcome to H&T Presspart, a market leader in the manufacture of respiratory drug delivery devices and components. Today, we would like to introduce you to our plasma PMDI surface treatment manufacturing facility. Our patented plasma treatment process helps reduce drug degradation and adhesion and improve inhaler performance. Once our MDI cans have been pressed and cleaned, they are placed into a bowl feeder at the start of the plasma manufacturing process. The cans are then fed along a conveyor belt into the jig placing machine. The cans are then automatically placed into the jig until it is full. One jig holds 600 cans. The jig is then transported onto the monorail through to the plasma processing clean room. The robotic arm then collects the jig tray and transports it over to the plasma pod and places the jig into the pod. The cans are placed with an electrode inside each can. Pressure in the plasma chamber is reduced to form a vacuum. Process gases are fed into the chamber. RF power is applied to the electrodes. This causes ionization, which produces the plasma. This is deposited as a nanolayer that is covalently bonded to the internal can surface only. Once complete, the jig is removed from the pod and placed back onto the monorail, where it is transported back through to the jig unfilling machine. The cans are then automatically removed from the jig by the machine. As the cans flow along the conveyor belt, they are 100% inspected for the presence of plasma by a camera vision system. The cans are then packed and placed into our warehouse, ready for shipping to our customer. Numerous quality control tests are performed on our plasma cans. The first being a dyeing test, which quantifies the surface energy of the can. The dyeing ink is applied and the plain aluminium can wets and the plasma can beads, showing low surface energy. The second test is copper sulfate. This checks for a uniform and robust surface. The solution is poured into the cans and left for 1 minute. After this time, the plasma can has no reaction to the copper sulfate and the plane reacts. The final test is contact angle, which tests the repellency of plasma using a tensiometer. A water droplet is placed onto the can base, which appears more rounded on plasma cans, so having a higher contact angle, and less rounded with the plain can, so having a lower contact angle. We hope you enjoyed our tour of our plasma manufacturing facility. You can find out more on our website at www.presspart.com.